Hello everyone, I'm DASARI ABHIJITH Reddy from Engineering Physics 3rd year IIT Roorkee. Today, the topic for my presentation is LVDT, which stands for Linear Variable Differential Transformer. So basically in this presentation, I'm going to walk through the experiment that I have performed in Applied Instrumentation Lab. So we are going to start from the objective of the experiment. Next, we are going to the apparatus required for performing the experiment. Then let's see some theory so that we can understand the experiment a little better. Then the observations, the results and conclusion, and last but not least, a new innovation to the experiment. The objective of the experiment is to study the performance characteristics of a linear variable differential transformer for both modulated and demodulated output. The apparatus required for performing this experiment are broadly divided into two subsections. The first section consists of mechanical unit, which is mainly the LVDT, which has the provision for the movement of the iron core. Next, coming to the main unit, where it consists of all the devices for doing the measurements and which is helpful for taking the output. We have the carrier and the signal amplifier. We have a demodulator. We have a 3.5 digital panel meter to show us the output. We have an IC regulated power. We have a D-type connector. And last but not least, we have a cathode ray oscilloscope. I'm also going to show these apparatus that we have used in the video too. Let us now understand how an LVDT actually functions. Here is the schematic diagram of an LVDT from its side. LVDT consists of a primary coil which is connected to the AC input voltage. It consists of two secondary coils which are connected to the output. Now these three coils are arranged like this, and an iron core is placed in between them. This iron core has the privilege to move, and it is the displacement of the iron core that we actually measure and that we actually need. And this is measured by using the difference voltage, which is defined as the difference of the potential differences between the secondary coils. So LVDT is based on the principle of electromagnetic induction. The electromagnetic induction happens between the two pairs of coils, the primary coil and the two sets of secondary coils. Due to the motion of the core, as the core has a higher permeability, the mutual inductance, as it depends on the permeability of the medium in between them, the permeability increases when the iron core is more towards the first secondary coil, and as a result the difference will increase as the iron core moves towards the ends. This will be clear in the figure on the next page. The diagram in this page shows the flux linkage in an LVDT. This part of the diagram shows the LVDT when the displacement is at the null position, when the iron core is at the null position and displacement is 0. As you can see now, the inductances, the value of the mutual inductance measured at between both the coils are actually same at 0 displacement. But when the iron core moves to one of the sides, the value of mutual inductance between one of the pairs increases and the other pair decreases, as the permeability here is more, and we know that mutual inductance is proportional to the permeability of the medium in between. Here is the panel diagram of the LVDT setup that is used in the laboratory. Now, the modulated signal is multiplied with the carrier signal and is then passed through the low pass filter to get the demodulated signal, which is obtained in millivolts. This is the demodulation process that is used. When we plot LVDT output with the input displacement, the value of the voltage observed at the null position is non-zero, and it's known as the residual voltage. This is obtained due to the unbalanced electric or magnetic fields present in the system. At zero loading, the LVDT output is calculated using the formula E0 equals to EC into M1 minus M2 by LP, and the output is obtained in volts. Here, EC is the carrier amplitude, M1 is the mutual inductance between the coil P and S1, and M2 is the mutual inductance between coil P and S2. LP is the self-inductance of primary coil. P is the primary coil, S1 is the secondary coil 1, S2 is the secondary coil 2. Here the values EC, M1, M2 and LP are given, and hence we can calculate the LVDT output at zero loading. Now let us take a look at the video that I have taken in the lab. The apparatus used for the experiment is the signal conditioning unit for generating unmodulated output, the cathode ray oscilloscope for modulated output, the LVDT with the movable iron core. The wheel is used to move the iron core. Now we switch on the equipment. As we can observe, as I change the displacement of the wheel, the iron core using the ring, and as I rotate the ring, we can see the displacement is changed as the values are changing on the panel. Now as I increase the displacement, we can see the values increasing on the panel. The readings are taken at an interval of 1 centimeter till 6 centimeters. Also notice, as I reduce the displacement now, the values on the panel are getting reduced, and now it falls to negative values too. Now as I further reduce the displacement to negative values, we can see the panel is showing more and more negative values. Also notice the connections in the circuit. Now coming to the modulated output case, we can see the value over here, 600 millivolts. It is clearly visible. These are the observations that I have obtained after performing the experiment. I have changed the input displacement of the iron core with respect to the null position from -6 to 6 with a step size of 1. The modulated output E0 is obtained in the cathode ray oscilloscope, and the demodulated output is obtained after the demodulation process. Both have their own respective units. Based on the observations obtained, I have plotted a graph for the modulated output and the input displacement, and also for the demodulated output with the input displacement. The input displacement is plotted on the x-axis in both the cases, and the output is plotted on the y-axis in both the cases. Now coming to the first case for modulated output, we can see that there is a linear trend observed in the graph between the region -5.5 centimeters to +5.5 centimeters. After that, the graph becomes non-linear. Also notice that there is a non-zero residual voltage in the case of a modulated output, which is due to unbalanced electric or magnetic fields present in the system. Coming to the demodulated output case, we can see a clear linear trend from -5.5 centimeters to +5.5 centimeters. Also, if we compare both these graphs, we can see that for modulated output case, the output values are always positive, but for demodulated output case, the values are both positive and negative. The trend is linear within the range -1, -5.5 to +5.5 as I've mentioned, and it becomes non-linear after that. Coming to the results and conclusion of the experiment, we can see that the graphs agree with what we have expected. For LVDT with modulated output, the LVDT coefficient delta E naught by delta X as a value 0.36 volts per centimeter. It has a linear range from 0.04 volts to 1.88 volts. It also has a residual voltage of 0.04 volts. Coming to the LVDT with demodulated output, it has an LVDT coefficient of value 34.8 millivolts per centimeter. It has a linear range from minus 193.8 millivolts to 179.8 millivolts. So the innovation for this LVDT experiment is I will be fitting a motor here, and the precise motion of the motor can be monitored here, and we can measure the rotation of the motor as precisely as possible by the rotation of this wheel. And as we can measure the displacement of the LVDT here, we can get the speed of the motor using this. But as here I cannot drill a hole here and I can't fit a motor, we were asked to suggest an innovative idea with the existing equipment. My idea is as follows. On screen we can see a setup where we have the LVDT attached to a motor. The LVDT's movable core is put within a tube which has the threads of a screw. Now the motor is adjusted in such a way that the shaft of the motor is connected to the movable core. Now as the motor rotates, the movable core moves forward through the tube which has the threads of the screw. Now this setup can be used to measure the angular speed of a motor. Now this measurement is really precise, and it can be made more precise using the ring which we rotate to get the displacement. The movable core is put within a tube which has the threads of a screw. Hence we can precisely measure the number of rotations done by the axle in a certain amount of time with the LVDT and the wheel acting like a screw gauge. Thank you for listening.